So we're going to look at the conservation of energy. We've talked about all the forms of energy, or some of the forms of energy, and made a map. We are right now worried about kinetic energy and gravitational potential energy. We will later add energy that is stored in springs, but for now that's the two we're interested in. So kinetic energy, gravitational potential energy, and of course the work, which is just a transfer of energy from one form to another. You can't destroy energy, so you can only transfer it, and the amount of energy transferred we call the work. Okay? Mechanical energy is going to be all the energy associated with the position and the motion of an object. So energy that has to do with where it is located and how fast it's moving is going to be called mechanical energy. So if I have a gallon of gasoline, that has lots of chemical energy, but the chemical energy is not associated with whether the gasoline is moving or not, or whether it's high up or down low on a hill. So that's not mechanical energy. Okay, so mechanical energy is energy associated with position, so that's gravitational PE, and motion, that's kinetic energy for right now. Okay, so we can say the mechanical energy is the sum of the kinetic energy and the potential energy. So in lab, you guys analyzed a pendulum as it swung back and forth. And what you noticed was that the kinetic energy started off at 0 because it wasn't moving, and then as the pendulum swung down, the kinetic energy increased. And then the kinetic energy decreased, and it eventually was 0 again when you're at the other side, and then it swung back. At the same time the kinetic energy was going up and down, the potential energy was going down and then up. The cool thing, though, is that if you look at the total energy, if you add the kinetic and the potential together, as that pendulum swung through its swing, the total energy was pretty much the same the whole time. Okay? It never really changed. And so when something doesn't change over time, we say it is conserved. We say we want to conserve the Grand Canyon, which means we do not want it to change as time goes by. So something that it does not change as time goes by, we say is conserved. And in this case, the total energy of the pendulum was conserved. The energy changed forms from kinetic to potential and back, but the total energy stayed the same, the mechanical energy. All right? So that leads to the conservation of energy principle, and that is that for an isolated system, the energy always remains the same. An isolated system is a system that doesn't interact with anything outside of its environment. So energy cannot be created or destroyed. We can only move it around from one form to another. And if we have an isolated system and we can track all the forms of energy, then we can say that total energy is conserved. So if we have a system that is not isolated, then the energy at the end will be whatever you started with plus any transfers. So we're going to write that like this. The energy at the end of the problem is going to equal whatever you started with plus any transfers, which kind of makes sense. If you start with 100 joules of energy and there's no transfers, you would expect to have 100 joules at the end. If you start with 100 joules, but you add 50 joules, then you would expect to end with 150. Okay? So this is the big idea. This is called the conservation of energy principle, or this is called the work energy theorem sometimes. All right? And it is not on your AP exam reference sheet, so you've just got to make sure you understand the big idea, that the energy at the end of a process is equal to the energy at the beginning, plus any transfers into or out of the system. Our sign convention is as follows. If we add energy to a system, then W is positive, which would make the final bigger than the initial. If energy is removed from a system, then W is negative, which means you take what you start with, 100 joules, you add a negative 50, and you end up with 50. So work is negative if energy is removed from a system. Okay? So I'm going to solve four example problems in 4 separate videos to apply this principle. It's tempting to skip those, but you should definitely watch them because they show you not only how to solve the problems and apply the ideas, but they also show you how to structure your solution. Okay?